We're continuing the discussion for the CMOS power, and we said last time that CMOS power can be divided into um, dynamic power due to circuit activities and static power, which is irrelevant in the most part of the circuit activity. The static power can be explained better. Let's just draw the CMOS device here, and we'll just explain it on the NMOS device. And so here is the N plus source and plus drain, and you have here the silicon dioxide and then the poly. Okay, and um, let's say we have three type of leakages, and the first type is called subthreshold leakage. And the subthreshold leakage happens because of the following. Supposedly, when the device is off, there is a 0 volt here, which makes there is basically no channel here to conduct, mostly depletion, um, and so you don't have electrons here. Okay, uh, basically you have depletion, and next to the depletion those holes. So the device is off, does not conduct current. Unfortunately, this is not true because even when the gate is 0 volt, there isn't anything called 0 volt in electronics. And in fact, you will see that if we probe this, for instance, if we put a probe here and um, plot it, okay, so here is the 0 volt. People expect to see this 0 volt here. And in reality, what you see really is more of that the voltages goes up and down, up and down, up and down based on circuit activities. And that up and down partially allow few electrons to be established here and run from the source all the way to the drain. And this is This is called subthreshold. So that establish a current, a leakage, subthreshold leakage current. Okay. Now, um, again, we do expect when this device is off, nothing no current occurs, but that's not the case. We have a few positive voltages here, sits here, and that establish sort of this few electrons here, pull them to the surface, and have um, those electrons travel from the source to the drain, small quantities, and that is the leakage current, subthreshold leakage current. Now, the other subthreshold is, we call it the gate leakage. And the gate leakage basically happens when the device is on. And when the device is on, basically you do have current uh, from from the drain to the source, okay, but it's not subthreshold, it is the current, okay, and you have a positive uh, voltage here, and probably disconnect to the ground. And then what happened is that you have these electrons, you have this channel here, okay, so you have this channel. Let me see if I can see um, if I can. Uh, okay, so we have this current that goes from the drain to the source. This is in the case of the on device. And electrons are traveling from the source to the drain. Sometimes the electrons, what happens, they acquire a very high energy, and what they do, these electrons, they penetrate the isolating layer of the silicon dioxide, and they go all the way and penetrate to the gate, and that causes the gate leakage current. Okay, and then finally, um, we have the um, the um, uh, junction junction leakage, and basically you have these this let's just see here, if we erase this current here, um, you have basically um, the the there are parasitic diodes between the P substrate and the in plus regions for the source and the drain, and we know that the P substrate is connected to ground, and those are reverse bias, both these diodes, this one and this one. But nonetheless, there is a leakage current for a reverse bias diode, and that contribute to the junction. And this is typically very small, and we typically ignore this type of leakage. And actually, the highest leakage tend to be the subthreshold, then the gate leakage, and then junction typically is ignored. Okay, so this is kind of an introduction to or explanation of the static power, which is the second component, along with the dynamic power. So let's go back to our slides here. And the last bullet here, some circuits are ratioed, and those burn power even when they are in the on state. Example, the pseudo NMOS, for instance. Whenever you have this input high, so you have a direct current from VDD to ground. Uh, these kind of circuits are really discouraged nowadays, and they are used in very limited types of circuits, and because they draw this static energy um, when they are even switching the inputs. So uh, people are discouraged of using these circuits except for very limited cases like wide NOR gates and wide NOR gates for the ROM implementations, etc. Okay. Okay. Um, so here is how do you calculate the static power? Well, we calculate the static power simply by computing, um, summing all the leakage power. Okay. I'm sorry, all the leakage current, and we multiply it by voltage. But so now for the leakage power, so let's see how I sum the leakage power in the sense of the circuit that I have. Let me do a little bit of explanation here. That in this circuit, what they do, they are using a circuit of two VTs. So we have a design of 1 billion transistor, okay, and we want to estimate the static power for this design. This design uses part of it normal VT and the other part high VT. Well, why would you use normal VT and high VT? In the next few slides, we will see that one of the ways to reduce leakage power sub-threshold is to one way is to reduce the subthreshold current, and the subthreshold current is sensitive to VT. If you have high VT, you reduce subthreshold current. Notice here in the example, high VT, the threshold, the subthreshold current here is 10. Normal VT, which is less than the VT is less than the high VT, you have higher subthreshold. Of course, higher subthreshold current is not desirable. So we want to reduce the subthreshold current. Okay, so why don't we use everything high VT? Unfortunately, if VT goes up, well, here's the good news. Subthreshold current goes down. This is good. This is what we want. But unfortunately, um, you increase, you reduce the current, okay, which is unfortunately increase delay. So we have to be very careful of using high VT because it slows the circuit. Okay, so what we do for fast circuit, we use normal VT or low VT. For slow circuit, we use high VT because high VT will reduce for me the sub-threshold current, and normal low VT will be fast. Unfortunately, will have higher sub-threshold current. Now, typically current is expressed as follows. You have ampere per micrometer of the gate of the design. So we have to find the total gate of the design and multiply it with this factor here. Gate leakage, it relates to the on. So these are for the on devices, and the subthreshold is for the off devices. And this is very important because sometimes in the exam question we will tell you that assume that the off devices are 60% and the on devices are 40%. So you have to understand not all the devices will be on and off at the same time. Some of them will be on, some of them will be off. So you need the percentage. Junction leakage in this problem is ignored. Okay, so let's use here a blue color. Okay, so now, so what he wants to do here is that we will use the same. Um, uh, he's telling me that high VT is used in all memories and 95 of the logic. That's from the previous problem that we used for dynamic circuit. So here is high VT, right? We we have this is what? This is the logic, the 50 million from the logic times 12 lambda in the logic times 95%, which he told me right here, plus all the memories, number of devices, every device in the memory for lambdas. That again, these are lambdas from the previous question for dynamic power. Once I compute how many lambdas I have in the high VT, then I multiply the conversion between lambdas and micro. So that will give me what? That will be the total micron of the devices that use high VT. Now, normal VT, we have only 5% of the logic. We multiply those 12 lambdas because these are number of transistors. This is the conversion between transistor and lambda, and this is the conversion between lambda and micro. And we get the micro for what? For the normal VT. Now, we take this, okay, so let's use a different color here. Okay, now we take this micron, right, and we multiply it with this a factor right here. Okay, because I know for normal VT, this is the conversion between micron and and ampere leakage. So that's exactly what he did in the subthreshold. He added, okay, the normal VT, which is right here, okay, multiplied by 100. Then the high VT multiplied by a 10. Again, notice the 10 is coming from here. Okay, the 10 is coming from right here. Now, what he did, he divided the whole thing by 2. This is because he is assuming that half of the transistors are off and half of the transistors are on, meaning we multiply every quantity by 50%. So that give me the what? The leakage, the subthreshold leakage, okay, for the entire circuit. Now for the gate, it's a little simpler because all the devices will leak 5 nano per micron. So I have if I add this one and this one, I will get the micron for the entire devices, multiply it by the conversion factor. Don't forget to divide by 2 because 50% of the devices are on. Remember, gate leakage are for on devices. Okay, so if you divide by 2, you get what? 275 milliamp. Now, what you do, you add, let's get another color here. Um, you add the subthreshold current with the gate leakage current. So that is the total leakage. Multiply this, the total leakage current, multiply this by the voltage, and here you get the static power. Okay, all right. So this is the example which explains how I compute this for this particular example. Now, subthreshold leakage, as we said, it's very sensitive to VT. Notice when VT is zero point 0.3, subthreshold leakage, or just notice that they are for off device. The device is at the off state. Okay, zero point 0.3, 100 nano ampere per micro of the devices, micrometer of the devices. Zero point 0.4, 10 nanoampere per point. So what happened when you increase VT, right? Now, no, notice you see this reduction. Okay, so that's a decade of reduction for the subthreshold current. Okay, so higher VT is good because it reduces leakage current, but higher VT reduces the speed of my device. So I have to be careful when I use it for what devices. Okay, there is too much involved here, and I'm going to leave this as a reading material for you. And let's talk about controlling leakage. How do I control leakage? And obviously, when if the most important one of those leakage is subthreshold leakage. Subthreshold leakage is inversely proportional with VT. So if I increase VT, the subthreshold leakage decreases. So how do I increase VT? Okay, so see the relationship here. I want to increase this guy because it reduces the VT because it reduces subthreshold current. So how do I increase VT? Well, I increase VT. Typically, people use multiple VTs. Low VT for fast circuits and high VT for the rest of the circuits. And that's how you can budget your circuit. Another way, it uses what we call if you recall in lecture 4, we have the VT. Okay, so if there's the body effect, we say that VT equals VTO plus, okay, this is the body effect factor, square surface potential plus VSP minus surface potential. Okay, so if I increase VSP, I increase VT during operations. So how do I increase VSP? Okay, how do I increase VSP? Well, either you increase VS or you decrease V body. In both cases, what you are doing, you are increasing VSP, which increases VT, which reduces the subthreshold current. Okay, these are one of the methods that we use to control leakage. Gate leakage, on the other hand, it is for the on device, and it is current that leaks through the gate. And typically, we try to use um, some processes with high K dielectric to reduce that current. We do use multiple TOXs to reduce this current. Um, and obviously, limiting VDD should reduce this leakage current because these are electrons that are penetrating the isolating SiO2 and going to the gate. If you reduce VDD, you are kind of reducing the vertical potential, which pulls those electrons from the channel all the way to the gate. Okay, so this is another reading material. And junction leakage, basically, it is those reverse bias diodes, and we talked earlier that your textbook liked to split them into band to band and gate induced drain leakage. This is between the gate and the drain, um, and in all cases this is really ignored for the computation of leakage power. So how do we reduce leakage? Okay, well, here is my circuit here, and kind of uh, not switching. The problem of static power that comes from the leakage is that even if your circuit is quiet, you are leaking, the circuit is leaking the leakage current. So what do we do? So what people do is that when I have the circuit not switching, I separate the VDD of the circuit and the VDD of the chip by a sleep PMOS transistor right here. And this PMOS transistor is off when the circuit is asleep. This should reduce tremendously the current that is flowing through the circuit, and it ends up being leaked to the ground during sleep mode. And when we are activating the circuit, so we turn on these transistors and the circuit starts switching and working just as fine. Only problem is that this gate here, the gate load of this PMOS transistor adds to dynamic power, number one. Number two, is that turning on and off might require additional delay, and this is again these PMOS can slow down your circuit. So every method got its advantage and disadvantage, and the simulation typically is the metric that you would judge to keep this method or not keep. Okay, so we with that we finished our discussion of the power, which we covered dynamic power and static power for CMOS devices. Thank you very much.